We are recording. Cool. So let's see. I recommend that you try out your cameras. Like get used to having them on. Make sure they work because we're gonna have this exam on camera in 12 days, I guess. So it's good to find out if there's going to be any issues in advance. Everything that can go wrong will go wrong. Just to expect that. Oh, hey, there's some real people. Cool. Okay, so yeah, today I'm gonna teach about triple integrals. Any questions before I get into all that? Nope. All right. Because why are we talking about triple integrals? Well, this class started with double integrals. I mean, the whole thing with 20E is that we're doing the same things that you did in 20B, but with more than one variable. So we already did the 2-variable version of integrals. Today, we're doing the 3-variable version of integrals, which is a particularly important number of variables, right? Like, we live in 3 dimensions. So this is a very relevant number of dimensions to be doing computations in. And indeed, there's a lot of important calculations that end up being triple integrals. For example, if you want to find the mass contained in some region of space, like, I don't know, like what's the mass of this cup of coffee? Well, you would integrate the density of the coffee over this region. That would tell you how much mass is in this cup. Or let's say you have some charged object, it has electric charge. To find the total charge, you would need a triple integral. So anyway, there's a whole bunch of examples and applications of triple integrals. I just wanted to let you know before we get into them that they are a very important and applied topic. The problems can be kind of long, though. So let's start with the definition. Here's the definition of a triple integral. And remember when we started with double integrals, we first had to define them over rectangles. Later on, we moved to elementary regions. Analogously, we are first going to define triple integrals for, well, I guess you could call them boxes. It's like the 3D version of a rectangle. Then later on today, we'll get to more general shaped regions. So let's suppose for one that we have some continuous function f. And it's defined on some box. And when I say box, I mean a product of intervals. So if you look at what I mean by a box in 3D, it looks something like this. It's like what you get in the mail from Amazon, okay? So we can thus define the triple integral of the function f over the box B, and we are going to denote it by this with 3 integral symbols. The argument is the function, and we write dv as in differential volume element. Previously, we wrote dA for a double integral, so we write dv, or we might write dx, dy, dz. And you can see we sometimes suppress the argument of the f instead of writing it all out. It gets kind of tiresome to write out the whole argument all the time. So all 3 of these are valid notations to indicate a triple integral. None of those tell you how to compute it yet, but maybe you can guess because it's kind of analogous to what we did with double integrals. You compute them by just performing an iterated So this formula on the bottom is how you can actually compute a triple integral. And you just first perform the z integration. So I can imagine that there's some parentheses around the z. And then perform the y integration. And then perform the x integration. So you might be wondering, well, what's so special about z? Like, why did we have to integrate z first? And the answer is there's nothing special about z. So I will immediately show you that actually you can integrate in any order. Oh, by the way, what's here's kind of a slightly meta question. What's the derivative version of this fact that we can integrate in any order? What's the 20C fact that you learned that's like the derivative version of this fact that we can integrate first with z and then y, or first with y and then z? Anyone know? It has to do with partial derivatives. Rob?
If you take like the partial with respect to x and then with respect to y, it's the same as taking the partial with respect to y and then with x. Yeah,
the so-called equality of mixed partials is a famous, useful fact from 20C. And yeah, this is just the integral version of that fact. So the following theorem says that you can integrate a triple integral in any order. So if you think about it, we've got three variables, x, y, and z. So you have three choices for which one you integrate first. And then you have two choices for which one you integrate second. And then you have one choice for which one remains. That means there are 6 total possible orders of integration. So there's actually 6 different ways I could write the formula for the triple integral. And I didn't want to write all 6. So I wrote 3 of them right here. But like I said, there's 6 total. So I'll leave it to you to figure out what the remaining 3 ways that you could write them are. Like you can see here in the second one, I decided to interchange x and y. Or in the last one, I decided to integrate x first and then z and then y. So let's try it out. Let's just do an example. How about I integrate the function xy squared, and I do it over this box right here, 0, 3 cross 0, 2 cross 0, 1. So I already drew the box. The function, by the way, how many dimensions would I need if I wanted to visualize the graph of this function? Four. Yeah, that would be a 4-dimensional graph, which is beyond human comprehension, you know, unless maybe you take DMT or something. But yeah, for the most part, we can't visualize this, okay? So if a function is defined on 3 dimensions, then you would need a 4th dimension to actually like see what the graph looks like. So we can't even see it. All I drew was just where it lives, what it's defined on, its domain. Regardless, we can still just plug in the definition and do the computation. So let's proceed with computing this triple integral. The triple integral over the box B of the function f, or perhaps I should say of xy squared dv will equal. Now, I'm free to integrate in any order I want. How about let's see, I'll do dz, dy, dx. How about that? So z goes from 0 to 1. Y goes from 0 to 2. And x goes from 0 to 3. So let's see. We'll get this doesn't even depend on z, so it's pretty easy to integrate. Let's see, that's 0 to 3, 0 to 2. Well, just xy squared, I guess. So now integrating that with respect to y, that will be 1/3 xy cubed from y equals 0 to 2. And that is, we get 1/3 times x times 8. Dx minus, I'm not bothering to write minus 0. So let's see, that gives me 8/3 times 1/2 times x squared evaluated from x equals 0 to 3. That gives me 4/3 times 9, or 12. So there's a triple integral. We get 12. Any questions on this? So, analogous to what we did. And wait, what's this? Sorry. What's that video, Josiah? Oh, the hypercube? Cool. Yeah, you know, I almost thought of.
It's Neil deGrasse just talking about lower to higher dimensions and uses a cube, like starting off with a point and then a line and then a plane and then a cube, and then the hypercube is like progressing through the dimensions and what that would look like and why we can't actually imagine four-dimensional objects.
Yeah. Okay. Yeah. That is really cool stuff. Cool. Thanks for posting that. Okay. So, just analogous to how we did elementary regions after we did rectangles, we are now going to do 3D elementary regions. Sorry, it's trash day here, so I don't know if you all can hear the trash truck coming by, but I can. Anyway, so here's the definition of a 3D elementary region. It's a region in 3 space in which one variable lies between 2 continuous functions of the remaining 2 variables, which are themselves in a planar elementary region. So again, there are 6 total ways that this could happen. So I won't show you all 6, but let me do one of them. How about I'll show you the one here where z lies between 2 continuous functions of x and y, and x and y live in a planar elementary region. So this picture is from the textbook, and you can see that, let's see, x and y live in this planar elementary region. It means 2-dimensional elementary region D. Z lies between two continuous functions, gamma 1 and gamma 2. So gamma 1 would be the function on the bottom right here, and gamma 2 would be the one on the top right here, and Z is constrained to live in between them. Then the region in between them is an elementary region. Okay, so this whole cube-ish looking thing, that would be an example of a 3D elementary region. And if you wanted to then integrate a function over that region, here's the formula for doing so. You do an iterated integral where Z would go from the function on the bottom to the function on the top. And Y would go from, well, the function on the bottom of the planar elementary region to the one on the top. And then lastly, X would just go from the minimum X value to the maximum X value. So yeah, that's our formula. And it can be kind of tricky, actually. So often the hardest part about these problems will just be getting it into that form. So let's do an example where we put the unit ball, where we express the unit ball rather as an elementary region. This is a very important example, by the way, because obviously the unit ball is a very important standard shape. So let's take the unit ball, which is the set of points in space satisfying this equation. X squared plus y squared plus z squared is less than or equal to 1.
Could you scroll back to the definition for a second?
Yeah, sure.
Thank you.
Wait, this one?
No, like above that. And then above. Yeah, okay. I just want to read that real quick, and then I need to write something. Okay. All good. We can go.
All right.
Thank you.
Mm-hmm. Okay. Oh, did Rob have a question?
Sorry, that was just me raising my hand for the.
Oh, sorry. Okay. Okay. So let's try to apply this to the unit ball. Let me ask a question about the unit ball first. So here's your definition of the unit ball. Here's a picture of the unit ball. Yes or no? Is this equation true? Yes or no? I don't even want to say it. I want you to practice like reading it. The point here is if you can read that and if it's true. So yes or no, hit the yes or no button, if you will. The first thing, if you're trying to answer this yes or no question, is what the heck does this mean? That's the boundary of a region. This was when we put this little curly partial, it's the same as the partial derivative delta. It means the boundary of the region. So the the unit ball is solid, right? It contains the interior. The boundary is just the points actually on the surface. It's like the difference between the rind of an orange and the actual meat of the orange. So the boundary of the unit ball is all the points where x squared plus y squared is actually equal to 1 as opposed to less than. That is true. And we're going to use the boundary to express the unit ball as an elementary region. So if x squared plus y squared plus c squared is equal to 1, I want to find what z is equal to. So z squared will be 1 minus x squared minus y squared. And z will be, okay, so if I take the square root, I should never forget the plus or minus right there. It'll be the square root, plus or minus the square root of 1 minus x squared minus y squared. So that's, those are, I should say, that gives me two functions on the boundary of the unit ball. The plus corresponds to the function on top. Okay, so that's like the top of the sphere. And we can call that gamma 2. The minus corresponds to the function on the bottom. So that's like the bottom of the sphere. And we can call that, that's like our gamma 1. So that gives a function on top and a function on the bottom. How about where do x squared and y squared live? So x squared and y squared live in this range of values. Wait a second. We have a name for that set. That's the unit disk, which we've talked about previously. So unit disk is right there, and x, y live in the unit disk. That is to say, x squared plus y squared must be less than or equal to 1. You can see this equation doesn't even make sense unless x squared plus y squared is less than or equal to 1. So I've already done the unit disk as an elementary region. I don't think I need to redo it here now. So I'm just going to use that I've already described the unit disk as an elementary region. And what we found was that you can bound it on top by the function y equals square root 1 minus x squared. Okay. And we can bound it on the bottom by the negative of that function. That is to say, y equals negative square root of 1 minus x squared. So again, I've done this example before. If you go back a few lectures, you can find where we did that. So finally, we can see what the minimum and maximum x values are. Maximum is 1. Minimum back there is a negative 1. Okay, so let me test you all as to what a integral over the sphere would look like, right? Like, let's say I wanted to integrate some function, it doesn't matter what, over the unit ball, I would write it as a triple integral. And well, I'll just tell you it would be dz, dy, and dx. And I want you to tell me what the limits are. Who can tell me, how about what the outer two limits are for x? Someone tell me what these two limits are? What's this limit and this limit? Oh, someone said it. Good. Yeah, in the chat. -1 to 1. Good. Okay. So, yeah, x goes from -1 to 1. Okay. Someone else tell me, what about these two limits? Oh, nice, Nicholas. Okay. Cool. Yeah, that would be negative square root 1 minus x squared to positive square root 1 minus x squared. Okay, and then finally, the new ones are negative square root 1 minus x squared minus y squared and positive square root of all that. Cool. Okay, great. So I'm not going to actually compute this now. It doesn't look very fun, to be honest. I mean, depending on the function. Later on in this class, we're going to learn a better way to integrate over spherically symmetric regions like spheres using, sure enough, spherical coordinates. But yeah, so these can be a pain to actually do. Okay, so I'm not going to do one now. I'm going to, well, there's a big example I have to do at the end of today's class. It's going to take like 20 minutes. Let me just give you a couple more formulas. So if you let your argument equal 1 and you take a triple integral, that just gives you the volume of the region. Kind of like with double integrals, how we would get the area if you just plugged in a 1. And then we can thus define our average formula analogous to the two-dimensional version. Note that this is also equal to the triple integral of f dv over the triple integral of 1 dv, both integrals being over the region in question.
Yeah, why is the triple integral is the volume formula? Isn't the double integral supposed to be the volume formula?
The double integral of a function is the volume under the function. So this gives you another way to get the volume. Just like how, so remember how in 20b, the integral would give you the area? And then in this class, we learned that if you do a double integral of 1, you also get the area. So yes, there are two ways to compute area. And now that we've gone up a dimension, we see there are two ways to compute volume as well. Although with a bit of work, you'll see it's actually the same formula. Okay, so the main thing I need to do today is this one big long example. This is going to take a minute. So here's the problem, and this will take up the rest of the class. Is let's let t be the solid tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And let's find the volume of T, and then we're going to compute the average height of all the points in T. So I got on Mathematica and plotted T. That's what it looks like, but let me do it myself because this is something that you should be able to do. So draw. Your axes. So let's say there's the X, the Y, the Z axis. And let's plot where, let's say that there's 1, 0, 0, that there's 0, 1, 0, and there's 0, 0, 1. Okay, so there's my tetrahedron. If you compared it to this picture, you would see that like this is the x-axis, this is the y-axis, and this is the z-axis. And first, we want to find like the volume of the whole thing for part 1 here. Oh, before we do that, I want you to guess actually. So there's 2 parts to this problem. I'm going to do the volume, and then I'm going to compute the average height of points in the tetrahedron. And when I say height, by the way, I mean the z coordinate. So we're going to treat z as like the height direction. So I want you to find the average of all the z values of points in T, i.e., we want the average of the function f of x, y, z just equal to z. So I want you to guess as to what this average is going to be. Notice that the shape only goes up as high as z equals 1. The base is in the xy plane at z equals 0. And so average is kind of like, where does z spend most of its time in this shape? So let me just give you a Zoom poll. I want everyone to guess, because then afterwards we're going to see how close everyone was or how many people were able to guess correctly. So quickly give everyone this poll. And you don't have to get it right, by the way. Like just guess anything if you don't know. I don't necessarily expect everyone to get it. I'm sure probably most people are going to be wrong, actually. What'll be interesting is like how close was your intuition, and well, just how many people could guess what it was. Okay. There, that's what everyone guessed. There, that's what everyone guessed. You don't have to keep looking at that screen, but I'll just leave it up. And so at the end of the problem, we can go and look back and see how close everyone was to the right answer. So Now let me proceed to do it. I first need the volume because I'm going to need that for the second part of the problem. So for the volume, so this is for part 1. I want the integral of the function 1. Now, I need to express this as an elementary region in order to actually do any computation, which means I'm going to need the formula for this plane, this face, this one right here, the front-facing face in the picture that I drew. Now, that's a plane. It's flat. It goes through the points 0, 0, 1, 0, 1, 0, and 1, 0, 0. Let me give you a useful fact about planes, at least non-vertical planes. So any non-vertical plane can be written as z equals a plus bx plus cy. Okay, so it'll be a little bit easier if I just use that formula to figure out. I need to figure out what function this is. Maybe you can guess, but if you can't, you can just plug in the 3 points and figure out what A, B, and C are. So let's plug in, let's see, how about if I plug in 0, 0, 1, then I find that 1 equals A plus B times 0 plus C times 0, i.e. A is equal to 1. Let's see, how about at 0, 1, 0, I find that 0 equals, now let's see, A is 1. B times 0 plus C times 1. So apparently C is -1. And at 1, 0, 0, I will get 0 equals 1 plus B times 1 plus C times 0. So B is -1. So I actually found the formula. It's Z equals 1 minus X minus Y. That's that face. Okay, so one minus X minus Y, that's like my, what did I call it? Is it gamma? Gamma 2 of X and Y in the definition of an elementary region. It's the same as this space here. So that's like my upper function. The lower one is easy because the thing just lives in the XY plane. So the lower function is just 0. And we're going to need to look at the set where X and Y live. So let me just mention that down here, Z is 0, and that's like my gamma 1 of X and Y. Let me call this triangle D, and let's take a look at D, where XY lives in the XY plane. So here's the region where X and Y live, what I call D in that picture, if you can see it. Right, this is meant to be the Y and X axis. It's the bottom of the tetrahedron. So I need to express D itself as an elementary region. So I need the top, and I also need the bottom. The top is a line going through 1, 0 and 0, 1. That's the line y equals 1 minus x. That's like my phi2 of x. The bottom here is the line y equals 0. So that's like my phi1 of x. Finally, let's see, where does x go to and from? X starts at 0 and it ends at 1. Whew. Okay. I got all my bounds for writing the tetrahedron as an elementary region. So I can commence with the computation. So the triple integral of 1 dv over the tetrahedron will be, let's see, x goes from 0 to 1. So from 0 to 1. Y goes from phi1 to phi2. So that's from 0 to 1 minus x. And z, well, we figured out that it goes from 0 to 1 minus x minus y. 0 to 1 minus x minus 1. Okay, so any questions on the setup? This was the hardest part. Almost always, it's just setting it up. That's the hardest part. Well, if you have any questions, let me know. I'll just go and start doing the computation now. But let me know if there's a question.
So,
I can
Professor,
go back. Uh-huh.
so like, if we did this like in a different way, and we defined x as a function of y, like we defined at the beginning of class, that means we could switch dx dy if we had just different definitions.
Yep, sure, yeah, good point. In fact, can you look at this tetrahedron and say, could we have done the integration in any order? Like, was this, could we also have done x first and then y and then z? Or, yeah, in
It
fact,
seems more natural to do z as like the innermost one.
Yeah. That's probably what we are most used to. But also, though, just looking at the shape, it's like totally symmetric in all 3 directions. So indeed, you could do this one in any order that you want. So, okay, let's see. This is 0 to 1, 0 to 1 minus x. This integral right here will just give us 1 minus x minus y. Get 0 to 1. Okay, let's see. This is going to be 1 minus x times y minus 1/2 y squared from y equals 0 to 1 minus x. Okay, so I'm going to get 1 minus x squared minus 1/2 of 1 minus x squared. In fact, I can even cancel one of these and just put a 1/2 right here. So I've got the integral of 1 minus x squared dx. You can save yourself actually a little bit of trouble if you do a u sub at this point. So how about if I just let u equal 1 minus x, du is negative dx, and this, so then this turns into 1/2 the integral of u squared times negative du, so that'll be negative 1/6 u to the third. Which is negative 1/6, 1 minus x to the third, from x equals 0 to 1, which is negative 1/6 times 0 minus 1, which is 1/6. Okay, we got the volume. Remember, this we didn't even get to the average yet. This is just the volume. Average is coming up in part 2 of the problem. So the volume of this shape is 1/6. Actually, kind of, if you look at the picture, sorry, it almost looks like it takes up 1/6 of the cube, right? So that seems reasonable. Maybe you could stack it, fit like 6 of them in there some way, somehow. Maybe you could do that actually. Yeah, there's 6 faces. I bet you could. So anyway, I'm sure there's a nice geometric interpretation of the volume of this tetrahedron being 1/6. But now let's do part 2 of the problem, which is to find the average of the average height of points inside the tetrahedron. So now, to find the average of the function that's just equal to z. Okay, so that'll be 1 over the volume times the triple integral, which will be 1 over 1/6. And now, thankfully, I already did all the work to express it as an elementary region, so I don't need to like redo the finding of the bounds and all that, thank God. So I can just plug these right in. Yeah, let's see, we will get 6 times 0. Let's see, that's going to be 1/2 z squared from z equals 0 to 1 minus x minus y. That gives us 3. So, but the number that we get is going to be the answer, by the way. So we're coming up on seeing who guessed correctly for this problem. Let's see, integral of 1 minus x minus y squared. You can do this integral with another u sub, by the way. I think that'll make it easier. Where since we're integrating dy, the 1 minus x part is like a constant. So we're going to get 1/3 times 1 minus x minus y cubed. I'm skipping like a step here with the substitution. So I can explain more details about this. If you're confused on this step, hang around after class. Okay. So let's see, this goes from y equals 0 to 1 minus x. And let's see, cancel the 3. What do we get? 1 minus x minus, minus 1 minus x. And 1 minus x minus 0. This first term just totally cancels. That's 0. Oh, wait, I'm missing a cube. Sorry about that. Cube right there. Cube right there. So what do we have so far? Negative the integral of 1 minus x cubed. We can, again, do a u sub right here. U is 1 minus x and du is negative dx. And again, I can do more details about this in office hours if anyone wants to see. So I will get positive 1 minus x to the 4th over 4 equals 0 to 1. Hold on a second. Oops, I think I dropped a minus sign. Sorry. This minus sign right here belongs right there. Sorry about that. Put it right there and put it right there. Oops, I accidentally dropped that little guy. Sorry, so I was off by a minus sign. So let me fix that minus. So there should be a minus right there, which should be a minus right there, which makes this a plus right there, which makes this a minus right there. So we get negative 1/4 of 1 minus 1 to the 4th minus 1 minus 0 to the 4th, which is negative 1/4 times negative 1, which is 1/4. Whew. Man, it's a long problem. So we got 1/4. That's the average value of the height. Now, only 11% of the class guessed 1/4. A big number chose 1/3, which is a good guess, by the way. There's another problem for which the answer is 1/3. I would like to point out, however, that if you look at the picture of the tetrahedron, it spends a lot more time near the XY plane than it does up near 1 on the Z-axis. So the fact that it has more volume, like closer to the XY plane, should tell you that it should at least be less than a half. So right off the bat, I think that all the answer choices that I gave you, except 1/4 and 1/2, or sorry, except 1/4 and 1/3, could have been eliminated. And it turned out that it was 1/4. And anyway, I'm hoping that you can see like why it should be less than a half. And later on, we'll see what does in fact have average value 1/3. But that's it for this one. Yeah, it was a long problem. Thanks for sticking through it. So that's it, folks. See everyone on Friday, and I'll hang out to answer any questions.
Now is office hours. Is it okay if I ask a question about the homework?
Yeah, sure.
Okay. I'm actually looking at homework 5.3, and it's
Okay.
homework question number 5.
Okay, you know what? Before I do that, let me just ask if anyone had questions like about this part of the proof.
Yeah, I do.
Okay, yeah.
So-
Let me just
Yeah, for the first question, to find the V of t, the volume of this, why is the function of x, y, z is 1?
That's the volume formula. Is you stick in a 1 for the argument of the triple integral.
Does it work for every triple integral? Because after you integrated the first integral, it turns out inside it's just a z. And then after the second step, that's just what we learned from the previous lectures, using a double integral to solve the volume.
Exactly.
And I see what you did there. I see why you said that double integral and triple integral is kind of the same. So
Yeah.
my question is, what if the function of x, y, z is not 1?
Yeah, then you get a hypervolume, a 4-dimensional volume. It's a good question.
I'm asking that because in the example, it didn't say the function of x, y, z is 1. It didn't say, and it didn't mention.
Well, I said the volume. The first question was the volume.
Oh, okay. Yeah, okay.
Let me ask if there was anyone that was lost at the U sub part. Like, how the heck did I integrate this? Did anyone want me to talk about that one? How I got this, or how I got that minus sign? Did everyone see that was this minus sign? Oh, everyone's good on that. Oh, and Krishna, your webcam, if it just shows your face, that's fine. Oh yeah, and Ziyan is asking base times. I'll talk more about that later, Ziyan. Okay, Martin, what was your question? Can you?
My question was from the homework number 5 from 5.3.
You have it on the screen?
Yeah, I can share screen, but I mean, I gotta wait for you to be. Yeah, all right. Let's see. So you can see the homework. This is 5.3. Use double integrals to compute the area of a circle of radius r. So I started just like we did from the lecture of the previous class, where we had we knew that the area of the circle is pi r squared, and then we derived for little r, and we using a triangle we found it to be square root r, capital R squared minus x squared, where x was the changing of the radius, right? And we were able to get it all done within one integral. My question for this one is for the second integral, are we also doing the change within that r? What's going on there? I guess it would be better if I wrote it out. So if we had this, right? That's what we did in the lecture, right? Where we had a circle where we had the circle and from the center point, there's a right. We had X, R,
Mm.
R.
Mhm.
Right. And then we can substitute the AX. It was pi little r squared. And we wrote that to be pi capital R squared minus X squared.
Yeah, so that was the cross-sectional area.
Mhm.
Right, like the so this thing, where did that pi r squared come from?
That's the area of a circle.
Yes, right, because the cross section, so when we did that problem, the cross sections were circles because we were like slicing a sphere. What are the cross sections in this? Well, cross section is not even the right word because it's an area that we're integrating over. So the problem asks for the area as a double integral. So like they want you to write a double integral. What's, by the way, let's say you just have some, I don't know, some region D. What's the formula for the area of D as a double integral?
It's, can I write it? It's just D. And then dy
Yeah,
dx.
yeah, okay, so that's the type of thing they want for this problem. So yeah, it'll just be the double integral of 1. And yeah, sure, we can do dy dx. And then what?
And then we need to find the limits of D.
Yeah.
Yeah, so that's what I was saying, like for this was for the first part, isn't this like one of them?
Aha. Yeah, so in this case, your disk is a circle. And what's the way that we learned that you are supposed to do a double integral over a region? What sort of regions can we integrate over? What sort of two-dimensional regions did we learn how to integrate over?
I'm at a loss for words.
There were, yeah, we had 4 different names for all the different types. There was X simple, and there was Y simple, and then there was also just simple and elementary.
Right.
Yeah. So you have to express it in that form in order to use a double integral. So how do you want to express this one as an elementary region? That means it has some like function on top and some function on the bottom, or some function on the left and some function on the right.
So I get, so that's how it would differ from the previous example where we only had one integral. So like we still have, this is a definition, but we can like split it in half. And write an equation for here, which is using this limit, where this is like negative r, and this is like positive r. And then doing the same thing from here to here. Is that what you mean?
Close. So when we did this one, I was using this thing called Cavalieri's principle.
Yeah.
That was actually for volumes, kind of interestingly enough. That's like a really general method for finding volumes. This problem specifically wants us to do it in a certain way. It's good practice. So like, we'll stick to doing this problem the way that they want us to do it, which means express the disk as an elementary region. So that means, for one, is it X simple or Y simple? Or both, or neither?
It's both, isn't it?
It is both, yeah. So, you know what, I think the easiest way is probably treat it as a Y simple region, like what we're most used to dealing with. So that'll probably save you a little bit of confusion, is let's treat it as Y simple. So to treat something as Y simple means you need to find the function on top and the function on the bottom. Function on top and the function on the bottom. With Y being a function of X. Yeah, what's the function on? What function is this with Y being a function of X? We call that like phi2 of X is what?
I want to say it's this over here.
Yeah, good. You're right. Yeah, because like this distance is R, and X squared plus Y squared is R squared. Okay. Good. Okay.
Right.
So yeah, now you figured out one part of the description of the region. Josiah?
Oh, I was just putting my hand up for when he's done with his question.
Oh, okay. Yeah, Martin. So I think maybe that'll give you an idea then of what the limits should be here. And you'll also need these limits for the X integral.
Okay, so I found the limits for dy here already.
We found one of them.
Found one of them, and then for the second one, this is the part that was confusing me. What am I finding again? I found the top part for y, and now I need to find how it relates to the bottom half.
So for the X integral.
Yeah.
Here, in fact, you know what? Let me show you where I did this lecture. Here, let me share my screen here. can share at the same time. Can I share it this? Whoa, multiple shared screens going on.
Oh,
Ooh.
wait, I think I see it, because I related y in terms of x, and I need to relate it in x in terms of y. And then I can,
Let me show you the formula.
just your stop sharing.
Go ahead. Where was it? The formula, where the heck was it? Oh, here's the formula. Yeah, Theorem 4. Do you see my screen?
Yeah.
So this is from Friday's lecture. So you need the function on top and the function on the bottom. This is for a y simple region where this is the function on top and this is the function on the bottom. And x extends from A up to B. So the x limits, this is just the minimum x value up to the maximum x value. So what would those be for your disk?
I was muted. Would it be R?
That's the maximum x value.
Yeah. Because it's like the maximum would be whatever the radius was.
Yeah, that's the maximum one. And I guess I should get to Josiah here. I also think you should probably practice this a bit, right? Like I think you could probably figure this out. So I don't want to like do too much of the problem for you, because I think you could probably use some practice with it. But I'm going to give you a hint for this problem because you're going to run into another issue, which, well, it'll be an issue or not depending on how much you remember 20b. So you remember how to do trig substitution?
Yeah.
Oh, okay. I take it back. Then that part won't be a problem. Good. Okay. Because I believe there's a trig sub to solve this integral.
Okay. All right. I'll just look at a trig sheet then. That way then. All right. Thanks.
And by the way, yeah. And if you, oh, he left. Okay. Never mind. Cool. All right. Josiah.
So I kind of had two questions. One was on the homework for 5.1, number 7. I got most of it. I think I was trying to integrate using Cavaliere's principle, but I couldn't figure out how to express the height of the triangle in terms of x or
r. Do you have the problem on screen?
Yeah, sorry. Let me pull it up for you. Can you see it?
Yeah. Oh, yeah, that one.
Yeah. So what I was trying to do was basically use that little triangle on the inside, and then integrate over x from -r to r.
All right.
Using that triangle, and I figured out how to create to put b in terms of x and r, but I wasn't sure how to put that h in terms of x or r, and I wasn't sure if it was my trigonometry or if I was approaching the problem wrong.
Yeah, there's another trick to this problem. By the way, that letter, it's supposed to be a theta. There's like a typo in the book.
Yeah, I figured that was just the the letter for the angle right there.
Yeah.
But I trying to set it up as one integral using Cavalieri's principle, because I've never used it before, because I transferred in, and that was something they kind of like just skipped over because it's like you could just use a double integral. So yeah, this for me was difficult because I was trying to figure out how to apply the principle and approach it that way.
So does theta change, or is it a constant? Is theta always the same for every one of those triangular cross sections?
I didn't think so because the h is changing, and so that would change theta as you change x.
Well, let's see. So they talk about this this lumberjack who cuts a wedge out of the tree, and it says he does it at an angle theta. So where is that angle? Like they showed it to you in this picture.
Oh, I see what you're saying. So the angle can't change
Oh.
because of the way he cut it, and if you go along x, all of the angles have to be the same, facing out towards the y-axis.
Yeah, right.
Along the x-axis. So then, since that's one thing, you could express h in terms of that angle, and b, which you can express in terms of x and r.
So you're right about b, h. You're close with h. So how would you express h?
Well, theta is equal to the tangent of h over b. So I could say the arctan of theta times b, I think is what it would end up being, is equal to h. Or I guess I could make it simpler than that. I could just say that h is equal to sine of theta.
Close. You're close.
Sine of theta. Well, I think I would want b in there somewhere, because the change in x is gonna change that y value. Yeah, I think I can figure it out though. The angle changing was like one of the biggest barriers for me because it added another element that's changing. But now that I've seen the light, I think I can actually figure it out on my own.
Okay.
And then my second question was, you mentioned using triple integrals for things higher. I think yeah, single integrals, area, double integral. Yeah, you said using triple integrals for like something to do with electrons, and then some other like force, I think, or mass. You used it for mass. And I was just kind of curious how that works.
Sure. Yeah, man, that's what my dissertation was all about. I can talk about that for much longer than I'm sure you or probably anyone would want to listen. But here's the basic idea. It starts with the concept of density. So density is like mass. Let's stick with mass for a second. Suppose Rho is a function of x, y, and z, and is the density of some material.
I don't think we can see your screen.
Oh, sorry.
Stop sharing.
Okay, yeah. If rho is like the density of, let's say mass density of some material, like maybe water, it's how dense water is, like how many grams per cubic meter or kilograms per cubic meter in water or wood or air or anything. It might change depending on where you are. Like, for example, if you've got a tank of water, due to the pressure, it gets more dense the farther down you go, generally. Right? So like same with air in the atmosphere. The higher up you go in the atmosphere, the less dense it is. That's why it gets hard to breathe when you go up to a high elevation. There's not enough oxygen because the air is not as dense. So you can then take any volume. I don't know, let's say this is just some region W. If you want to find out how much mass is in W, that'll be the integral of the density. So that would be an example of a triple integral calculation that would yield the total mass that's contained in some region.
So then you just need a function that defines some kind of behavior that is modeled by, or that like exists inside of or a part of a three-dimensional object.
Yeah, so right, so yeah, mass density is one such example of a function that's defined on space. Temperature is another one. So if you wanted to find out like how much heat was contained in a region, you might want to integrate the temperature over the region. You might want the average temperature. Say like in a snapshot in time, you want to find the average temperature in this room. You would integrate the temperature at each point in space and divide by the volume of the room. So if T is the temperature at the point X, Y, Z, then if you integrate T over region, this gives you the average temperature in W. You could even add time, by the way, and make this a four-dimensional integral if the temperature was changing in time too. So yeah, you can keep playing this game. And yeah, so that's another example of a useful three-dimensional integral. If rho was, what if instead of mass, it was charge density? This is what my dissertation was all about. Then you would get the charge in a region instead of the mass. And what gets really sort of interesting or meta, if you will, is the fact that density, it only makes sense if you don't think about it too hard. Because at the molecular or atomic level, if you got a superfine microscope and looked at, I don't know, your table or your hand or your cup of water, you would see a bunch of atoms with like a bunch of empty space in between and electrons flying around in their electron orbits and dense nuclei of atoms that have protons and neutrons. And so what the heck does density even mean at that scale? It's hard to define. It would be a highly discontinuous function where, so the density of like a proton or a neutron is about as dense as a black hole.
Huh.
Right? But that's because atoms have a whole bunch of empty space in between the proton and the electron. So that's why we are not all crushed and spaghettified instantaneously, you know, because of all the space that keeps and other nuclear forces that hold electrons hold atoms at the proper distances from each other. But if you really think about it, density doesn't really make sense. So it's inherently kind of an averaging or coarse-grained concept. And if you really start thinking about it from a mathematical perspective, you have to start looking at fractals. So it makes sense to say that, like, oh, this square has area, let's see, length 1, height 1, the area is 1 times 1, which is 1. That makes sense. But what if instead of a square, you had something that had a whole bunch of holes in it? Like, let's say you took out a bunch of little subsquares, and then you looked at the space like between them.
Mm-hmm.
It's kind of hard to draw. And then you repeated that process of like cutting out even yet smaller squares. That would turn this into a fractal shape, where the more times you zoom in, the more times you see the same shape repeated. It would be infinitely self-similar. When that's the case, our concepts of area break down, and we can no longer really say like what the area is. There's different definitions, and they yield different numbers. So even the seemingly basic concept of area, and in math we would call it measure. So there's an entire field of mathematics called measure theory, which is devoted to questions such as this, such as making sense of the concepts of volume, length, area, and so forth. And it is a really deep field. Like, you can go so deep into that. If you read some measure theory papers, they get so highly technical. Like, I know a lot about measure theory, and I still don't know anywhere even close to like the depths of that field. And I probably know it more than any other field. So that is a very rich but very technical field, which, well, you know, this is the basic idea with measure theory, is trying to make sense of the concepts of length and area and volume. And what's cool is just how complicated they are, yet most people would never think about it until they think about it.
So basically, the math we use only works on like the macro level, but once you actually start to get into the micro, it starts to break down.
Yeah, right, exactly.
Okay, cool. Thanks, Professor.
Yeah, it's a fun question. Thanks for asking. I hope I didn't bore you too much.
No, that was, I mean, I like math, so this was cool.
Yeah, cool.
I have a question.
All right.
Okay. Yeah, my mind is still processing on what you just said. But anyway, it was the end of the calculations in the lecture.
Mm-hmm.
On the second question, it's basically what was he still here? Zi Yang asked. Zi Yuan, I think he said, isn't the question was find the average height of the point in T, right? Isn't that just like the volume divided by the area? You know, the base area?
Average height being the let's see. Yeah, I believe so. Let's see.
But
We
if
can
the-
check.
But if it is the volume divided by the area, then the answer is very different.
Well, it would be, you would integrate the surface, so that it should be the integral over the triangle in the base. This would be a double integral, right? So it should be let's call the base.
We can we can see it is 1/2 that area. Right, the base of the area is just 1/2.
Yeah.
It's a right triangle.
Yeah.
Right,
yeah.
and the volume is 1/6. And once you use 1/6 divided by 1/2, we get 1/3.
Let's see.
And also what I don't get is you kind of also like say that question is just basically mean the average.
Sorry. Okay, no. So what you found was the average of points on this face. Sorry. So I was it's not equal to the integral of the height of this face divided by the area, because what that would give you would be the average of points on this face, average height of points on that triangular face. In other words, let me look at the other picture. This one. So if you only considered points that live on this face and you asked what their average height was, that would be 1/3. And it would be the integral of that function, which is 1 minus x minus y, divided by the area of the base. So that's the average of a 2-dimensional surface. But we asked for what the average of the 3-dimensional solid tetrahedron was.
And can you explain a little bit more? How is the function of x, y, z equals to z over t is the average height? I just couldn't see or relate that function to the question.
Say the question. How is the function what?
How is the function that the way that you solved it is the triple integral of the function f x y equals to z over volume is related to the average height? I just couldn't see the connection.
So we wanted the average of this function. Z is the function that we take the average of. And the region.
So is that like the part of the question, or that's something that we have to figure out by ourselves, or it could change?
I included it as part of the question to make it clear because, well, having taught this class before, I knew that it was potentially confusing. So sometimes I'll ask a question, and in the question, I'll give some explanation as to what I'm asking. So here I asked for the average height, that is the average z value of points in T, not on the surface of one of the faces of T.
Inside of the volume.
Inside the volume T, right. Which I then clarified that what I'm asking you for is to find the average of this function.
What I can relate is the average of that function with the average height of the point in Z. Why is that just the average height?
I'm treating like the XY, treating space as having this being the up direction, kind of arbitrary. You don't have to have Z being height, but we often view things that way.
Okay.
So with that convention, I treated the Z direction as the direction to which I ascribed the with the adjective height, the attribute of height. So you could think of this tetrahedron as consisting of many points in the interior of the tetrahedron, right? Each point has some x value or some x, y, and z value. In particular, it has a z value, and I wanted the average of all of those. So imagine you took 1,000 points in the interior of this thing. That'll give you 1,000 heights. What's the average of those? Or what if you took 1,000,000 of them, or 1,000,000,000, or in the limit, you end up with the volume integral that we calculate.
I see, I see. So T is pretty much just basically it's like how many points are in there.
Yeah, I mean,
Right.
we call it, I think the word is like locus. It's a set of points. Yeah, it's all the points that lie within this region. In fact, if I had more time, I would have shown you the shape in Mathematica. Here, let me show you. I was going to show you. I plugged it into Mathematica, and I wanted to like move around on it so you could see it. You can see this is where I plotted it. Mathematica actually has just a function where you can just plug in the coordinates of the vertices, and it plots the tetrahedron for you. So yeah, there it is. And it's a solid. By the way, I think you might qualify for a student copy of Mathematica. Possibly. You might be able to have access to it as a UCSD student.
I know as a UCSD student, we have access to lots of software programs.
Mm-hmm.
Yeah, I'm using a lot of those, the Microsoft and also the MATLAB as well.
Mm-hmm. Yeah, that's a useful skill.
So where am I getting this is the triple integral of the function of x, y, z equals to z is basically like the Riemann sum of all of the z height, all of the z.
Mm-hmm.
Okay. Then, the Riemann sum.
And what that other student said about finding the average of just points on this face, that's a interesting and confusing point. But if you think about it, like, what's so special about this front face? Shouldn't we have also like averaged the side face and the back face and the bottom face? You know? So if at first it seems to make sense, but then if you think about it, it actually doesn't make sense.
I get it now. Okay, so when we're doing a test or exam or homework, for questions like this, do you always like clarify it?
Yeah, I try to, yeah, pretty much. Like I'll ask a physics question, but then therein I'll just give the equation that I'm asking for.
Got it. Okay, I see. Thank you so much.
Yeah, sure.
Hi, I had a question on problem number 6 on homework 5.2.
Okay. Can you show it on your screen?
Yeah. So it's asking for the solid whose volume is given by this. And originally I drew this on the left, but I figured it kind of didn't make sense because, I don't know, there wasn't like a point down here, I guess. So then I drew the figure on the right, but I'm having trouble figuring this out. Sketch it.
Yeah, those are nice drawings. Wow, you got nice notes. Yeah, I think your drawing on the right is pretty good.
Okay.
Yeah, I think your drawing on the right is pretty good. That's probably about as good as a drawing for this could get. Pretty much. I mean, oh yeah, you're using OneNote too. Yeah, I mean, you
Yeah.
basically got the idea. It looks like a parabola as it approaches the origin, but yours looks pretty close to that, so it's not a big deal. By the way, z equals 9 plus x squared plus y squared. There's a name for the shape of this graph. Do you know what that shape is called?
Paraboloid?
Yeah, right. Exactly. Yeah. So like a 3D parabola.
Okay. Yeah, I was just confused because like in the first drawing, like it didn't make sense to me because there was like this point at the origin and like I don't know why, but I think it makes sense now.
Okay. And here's another tip for figuring out drawings is you can do drawings by cross sections. So like pick a value for, let's say, y and see what x looks like. So like if let's say if y is 0, then you get z is 9 plus x squared. So that's your y equals 0 cross section, which is exactly what you started to draw right here.
Oh, okay.
And then if y is equal to 1, you'll get what is it? 9 plus x squared plus 1, or 10 plus x squared. So that would be if I see, how could I draw that? That would be like something like that at the point where y is 1. See what? Yeah, something like that.
Okay.
Or wait, actually, no, I didn't quite draw that right. Oops. It's hard to draw. It's supposed to do something like that.
Okay, I can see it.
But yeah, it's like a piece of a parabola.
Okay, that makes sense.
And you could similarly do cross sections where you fix a value of x. But yeah, what you did is fine.
Okay, thank you.
Mm-hmm.
Have a nice day.
I actually was going to ask you for some like pointers on how to go about drawing 3D shapes.
Yeah, it can be tough. So I have a few.
I wouldn't bet my life on it being able to draw some of these things. But I'm like, is there like things that you should do specifically, like in terms of putting things in front as solid lines and putting things in back as dashed lines and stuff? Is there any sort of, kind of set rules for that or not?
Yeah, that's a habit that I got into kind of informally. Like, I don't remember ever reading any rule that said to do that anywhere, but I just found that it was kind of useful for visualizing. Like here's a a trick that I do a lot, which is pretty helpful, is here. It's what I did with this thing right here, is draw the dotted.
I feel like I never know like where to put it. Like which ones get, I guess, the dotted line and which, you know what I mean?
Yeah, so I'll use the dotted line when it's in like the back of the shape.
Yeah.
And there's a number of tricks that can help. I just mentioned one to Denise about cross sections.
Yeah.
And
that's kind of what I did on that problem that you guys were just looking at, is like I drew my rectangle on the ground and then I drew it as like a grid and determined like what the height, what my Z value would be at each section, so at like 1, 1, at 2, 1, at 1, 2, I determined what the Z value would be and wrote it on that kind of like bottom level, and then tried to just kind of draw that up in the Z section.
it
looks nowhere near as pretty as Denise's did.
hers was nice, yeah.
I literally was like, holy cow. I look like a 3-year-old drawing compared to what she had.
Tell me about it. Yeah, I do not have an artist's hand myself either. But there's also those like rules for drawing in 3D, where like if you want to do the point, I don't know, like 2, 3, 2, you would go 2 in this direction and then count 1, 2, 3 in this direction, and then like go up to that direction. So when you move parallel to the axes. That is kind of a rule.
Okay.
How
do you know then, like oh God, it's hard to describe without like having like if you were trying to draw something that was floating, was not in any way touching the XY plane, like how do you know which ones do you connect out front to be the sort of surface that you would be looking at from this angle that you have it at? Does that make sense?
Some can be tough. Let's see, like you mean like if you were looking at like a sphere or an
like if you were looking at like a wedge of cheese that was floating above the XY plane, and was so it's off Z, like Z at say the bottom of it was at Z equals 2, like would you basically like kind of I guess I'm trying to ask like which points would you connect together as a solid line to indicate that that's the closest portion that you're looking at? Like that's the part where I kind of am like, I don't know which ones to put together to indicate that they are closer to the viewer as opposed to ones that would be behind.
Let's see, like a wedge of cheese. So yeah, that one can be kind of hard. Like that.
Okay, yeah. Yeah, I mean that's a sheep that I'm thinking of. I'm just like, I don't know which ones, like in my brain, I'm like, oh God, like which ones do you connect together to indicate that they're closer, and which ones would be the dashed lines that are sort of, giving the representation of them being behind. That's the part, like every time I try to go to draw something, I'm like, oh God, I don't know which ones are gonna come out to look the way I want them to.
Yes, I'll do it with edges for one, and then yeah, like if it's a shape that is behind the volume of interest, then I'll make it dotted. You can also get some help from graphing utilities. So, this is a modern age. It is allowed and permissible and even encouraged that students in this class do try out some software. So I haven't really pointed out very many like graphing utilities or websites, although I probably will at some point. But if you just
came across a couple like trying to do, I used to use Desmos, but I feel like I couldn't get it to do what I wanted. And so I just found another one and just was kind of doing it off of that. I think I'm actually using a site similar to this.
Yeah. So this one has a nice like graphing capability. Oops, that's not what I wanted. Let's just do a paraboloid there. So yeah, there you can do a paraboloid pretty easily.
Okay. Okay.
So yeah, this one is a good way to visualize when you can't figure something out. Also, there's also just certain shapes that are standard too. Like this one is a paraboloid, and any variation on like 2 plus 3x squared plus 6y squared would be another type of paraboloid. And you also have hyperboloids like x squared minus y squared. Those are cool.
Yeah, if I don't have to draw them, they're cool.
Yeah. This is like a horse saddle. It's a good illustration of negative curvature, which is, I think, the Einstein hypothesized that space is curved, so you can actually have due to gravity, you can have space that curves away from itself, kind of like this does, except in 3D instead of 2D.
Yeah, I took a class at my community college that was almost essentially exactly this course, and our teacher would call them the Pringle shape.
Yeah, right. That's a good one. It's a better.
Yeah, it was very much like, oh, I know exactly what that looks like. Okay. Just really quickly, so I spoke with the OSD liaison for the math department. So I am gonna just, email her, and then she'll facilitate with you. Really, the only thing is I get the extra time during exams. So it's specifically so that I can take breaks during the exam. So I know that you're gonna have us on camera, when we're taking our exams. So I have to physically walk away from my computer when I take a break to deal with my medical stuff.
Okay.
So if it's all right with you, I'll just send you a private message and let you know when I'm going to take a break and what time I'm going to return from the break. Does that work for you?
Yeah, that's fine.
Perfect. Okay, so yeah, I'm gonna email her when it's closer to the time, and she'll get in touch with you about it. But I just wanted to check in with you for that.
Oh yeah, okay, yeah. Thanks for letting me know.
Yeah. All right. Well, I'm gonna head out. Have a good rest of your day.
All right, cool. Yeah, you too, Patricia.
Bye.
All right.